was CopyEye. And this program costed 370 hours of Herschel time. So the goal of the program was thermal observation of KBO and centaurs with the 2 photometers of Herschel. As you know, probably Herschel was a 3-meter sub-millimeter telescope that flew between 2009 and 2013. And what? It's still flying, yes, but it's mute. And so PACS covered the 3 wavelengths, 70, 100, 160 micron. SPIRE covered 250, 350, and 500 micron. And surprisingly enough, the goal was to measure size, albedo, and thermal properties. So the goal was for size and albedo was to reach what I call a large sample of objects. Large actually means small, but larger than what had been done before. And actually, we did 130 objects. One of the goals is that we need an albedo database that's needed in particular for a proper interpretation of SPRA and other physical observation. But also an important aspect was to search for correlation between size, albedo, and other physical parameters like composition, color, binarity, and with orbital property, because such correlation might tell you something about origin or evolution diagnostic. And also perhaps obtain constraint on the size distribution for large objects that are not affected by collisional evolution, objects larger than 100 kilometers, and that are typically within the range of the observation. The other properties are the surface property, the thermal inertia, roughness, spectral emissivity. Also, we created a number of binary systems with known masses. So if we have the total mass, we can have the equivalent size. And if we can measure the equivalent size, then we'll get the density. We also obtained a few detailed studies for some emblematic objects by measuring light curves, and Pablo will discuss this. So this program, in fact, was a follow-up of Spitzer similar observation and 24 and 70 micron that obtained about 75 good or satisfactory detection. And so with Herschel, we have almost double the sample. So the approach, as I said, PACS and SPIRE, but we use PACS heavily for the whole sample of 130 objects, SPIRE only for the 10 brightest objects because of sensitivity and confusion issues. Note that the sample was built based on flux expectation, based on the Spitzer-derived results, and of course, there was a strong bias towards the easier objects. We attempt objects for which we had a good chance to detect them, not to waste telescope time too much. And of course, it's very biased towards the closer and optically bright objects. Whenever possible, which was actually quite often, the measurement with Herschel was combined with a measurement with Spitzer, and it was extremely useful to determine the thermal regime of the object because Spitzer at 25 micron, of course, gives a large leverage arm for fitting for example, the Nikon. So for analysis, we used modeling, diameter, albedo, and either a NITM in terms of a beaming factor or a thermophysical model in terms of thermal inertia, surface roughness, and pole orientation or rotation period whenever known, which is typically not the case for TNO. Or when it's known, it can be explored, as I will show you one example. There are a few measurements of diameters in the Kuiper belt from stellar occultation, and this gives a nice validation of the radiometric method. So we know it works on asteroids, but it's also an example where it worked rather well with very few exceptions. So this shows for most of our objects the diameter in our sample plotted as a function of heliocentric distance. I am just showing this to illustrate the range of sizes we are sensitive to, typically to 10 to 1,000 kilometers, but especially to show the very strong bias that we have in our sample, with only the smallest object being reachable when they are close to the sun, so typically the centaurs. This is a plot now of the ensemble of diameters and albedo in our sample. So the albedo range from very low values, typically 3%, to essentially 100% values. There is not really a correlation between the diameter and albedo, but one feature here is that there are no small objects with large albedos, which can be probably understood that small objects are unable to retain any ice, so which make their surface dark. So despite this huge variability in surface albedo, the H magnitude remains a reasonable proxy for size. This is a correlation between the diameter and the HV magnitude. And you see it's best fit with a mean albedo of 10%. So 4% should not be used for TNOs, by a mean value of 10%. And of course, there are departures from this mean 10% value, and especially the high albedo object that you see on the right. These are the large objects, very high albedo. And these consist of volatile covered objects like Eris or Makemake, or the Haumea, very bright surface water ice covered objects, Haumea and its collisional family. This plot shows a distribution of albedos as a function of population families, and this is actually a cumulative distribution histogram. And you see that, in fact, the different dynamical families have different albedo distributions. So from the darker to the brightest, we have first the centaurs and the scatter disks, so shown here in green and in dark blue, and they have very similar distribution. And then we have slightly brighter, we have the Plutinos that are also similar to the hot classical. Then a little brighter, the cold classical and the outer resonant objects. And then the brightest of all families are the detached objects, which are shown in pink. So there is some differences between the different population. The fact that the centaurs and the scattering objects have a very similar albedo distribution is perhaps not surprising, because centaurs are often thought to be produced from the scatter disk, but it probably also it means something that when these objects enter the inner solar system or the region of giant planet, they don't undergo a change of albedo or of surface properties. So it tends to say that the surface properties are more primordial than recently acquired. One of our most interesting results, I think, is the evidence for a grouping in the albedo color distribution. So this is a work done by Pedro Lacerda. And you see that, in fact, if you plot here the albedo as a function of the spectral slope that indicates the color, you have two groups of objects. If you exclude, of course, the very bright volatile ice-covered objects I mentioned before, you have a large group of bright and red objects and a smaller group of dark and neutral objects. And this separation is fairly clear. In fact, you can do different tricks, mathematical methods to find for groupings, and it robustly finds these two groups. And this is interesting because it probably tells something about the origin of colors in the Kuiper belt. There is one idea that's due to Mike Brown and colleagues that, in fact, the colors are primordial in the Kuiper belt, in the sense that they were acquired since their formation. The idea is the following. So the Kuiper belts form as a mix of ices of different composition. And then when the solar nebula vanishes, the solar hits the surfaces. And depending on the surface of formation, only the less volatile ice can be retained on the surface. The most volatile ices are lost. So then what happens is that the ices that are retained are irradiated, and in fact, rather quickly, in 10 million years or so, they acquire their colors, and then a crust will be formed, and the colors will be kept, whatever any dynamical evolution. So in this scenario, the colors are formed primordially. And in this scenario, methanol plays an important role that was proposed by Mike Brown, because from lab measurements, methanol is known to redden and also probably to brighten under irradiation. So in this scenario, in fact, the bright and red objects that we see, these two groups, could be the objects that were formed beyond the snow line of methanol. So they were formed far when methanol was stable, and then they became irradiated, and they are now will be seen as the red surfaces and with high albedo. So in idea, it's interesting to see that to reduce this two-group plot as a function of dynamical family. And you see that for most dynamical families, in fact, the objects are shared between the two groups, the red bright group and the dark neutral group. But there are exceptions. The detached objects, the all classical objects, and the outer resonance, all the objects are located in the bright red group only. So this means that this family of objects were probably formed beyond the methanol snow line, if the scenario of Brown is correct, while other family of objects were formed anywhere, and they then reshuffled to their current orbit by the dynamical evolution of the Kuiper belt. So this color albedo correlation has probably some significance as to the formation of the objects.
Dynamically, those low are the most stable.
Yes, so they were probably were from where they are now. Yeah. Yes, correct. It's consistent with that. Yeah. Now changing topics, I mentioned most of the measurement was done within PACS, but we also use SPIRE for a small number of objects, about 10, and SPIRE extend the wavelength range to the longer wavelengths. And so by combining the two, we can have a feeling of the surface emissivity properties of these objects. And so these are surface emissivity in the sense that the observed flux divided by the model, whether an ETEM or a TPM. And what is clear here is that for most of them, there is a large decrease of the emissivity longward of about 300, with, in fact, often the objects being undetected by the SPIRE observation. So it means that the brightness temperature of these objects are lower in the long wavelengths. And this is probably part due to the fact that the longer wavelengths progressively probe subsurface layers that are colder than the dayside. So although, in fact, we are not sure if this is completely due to a subsurface sounding effect or if actual scattering within the surface can occur. But observationally, the effective surface emissivity decreased with wavelength. Another result regards the densities. So we have a limited number, but still growing values for the densities. And what this program and other revealed is that there is a huge variability in the density of the Kuiper belt objects, with low values ranging from about 0.5 or even less, and high values up to 2.3 or more. So a difference between, and there is a correlation between the density and the diameter. So the small objects tend to have lower density than the large objects. This could partly due to a compaction effect of the large object, while the smaller will be more porous. But it's also possible that also the two classes of objects have different composition, with high ice to rock fraction for the small objects and low ice to rock fraction for the large objects. In fact, of course, this diagram is still very inaccurate. We are missing a lot of points. In particular, we don't know the transition regime between the two groups. And also there is this intriguing values here, the points that could be outliers, we don't know, where it seems that there are objects with large densities and low sizes. And we need to get better measurement on this kind of object to see if really this class of objects exists or not. Okay, I will now discuss thermal properties of TNOs. So this is one of the series. So the TNO projects has produced a series of papers, about a dozen, I think now. And so there was a paper dedicated on the thermal properties. And so the approach is the following. In principle, so as you know, to determine the thermal inertia, we need running a thermophysical model. But of course, the approach is severely limited if we have few data and or if the parameters are non-known, which is typical for our KBO observations. Although, I mean, you can do on a object-by-object basis, you can do systematic exploration through a TPM model. And this is an example that was done, in fact, this work was done by Thomas Müller. So you see here an example, this is Chariclo. This is the observed spectral energy distribution. Here on the first panel, you have an ETEM model, but then on the right, you have a TPM fitting, and this is a ratio of the data by the TPM solution. And then here there is exploration of parameter space. Essentially, you have chi-square residuals between model and observation as a function of thermal inertia for different values of pole orientation, surface roughness, and rotational properties. And in all these cases, you get thermal inertia that are low, with minimum around best fit for thermal inertia of about 10 or so. But of course, doing this in a systematic manner is rather heavy and not too easy. So another approach, of course, is to use the NITEM and statistically infer constraints on the thermal inertia for the distribution of the beaming factor. And Marco showed this the first day for his work on NEAs. And in fact, he claims this was his idea. But if you talk to Alan Harris, Alan claims that his idea. But, but because Alan is not here, it's Marco. So, hello, Alan. So here we followed this idea, and in fact, I used Marco's paper anyway idea to fit the ensemble of beaming factor in the TNO population to infer statistical constraint on the thermal inertia of TNOs. So we have 85 objects, enough thermal coverage that we can determine a useful beaming factor. And these are, of course, in general, the object for which we had both Spitzer and Herschel measurements. And so this is the distribution of the beaming factor as a function of distance. So you see values lower than 1 that are indicative of roughness. You see values that seal at a asymptotic value of about 2.5, which is in fact what you expect for a high inertia object in this range of distance. You see also a vague trend of increase of thermal beaming factor as a function of distance. And you see an empty region here. And this is also what you expect for a family of objects for which the thermal inertia is not too high. Another interesting result is that there is some kind of correlation between the beaming factor and the geometric albedo, in the sense that high albedo objects, so typically larger than 20% geometric albedo, systematically have a low, preferentially low beaming factor. Although we don't have many values in the range of high geometric albedos, essentially except for one object, which is Makemake here, there are very few objects with both high geometric albedo and high beaming factor. So coming back to the variation of beaming factor with heliocentric distance, a possible method is to specify some surface roughness, assume it's the same for all objects, specify a given spin rate, so spin period, spin orientation, and then invert systematically the eta values for thermal inertia. And if we do this, we get this distribution, rather noisy, but with an accumulation of points at low value of thermal inertia, typically 5 or so, and maybe with a decreasing trend of thermal inertia with heliocentric distance.
This is marked the way of the what I did it. This is marked.
No, this is not the way you did it.
No, exactly.
Yes, it's another way. Yeah, it's less good, so yeah. The way you did it is this one. So we make the other approach. We make a synthetic population of objects with randomly generated roughness and orientation. We fix the period because it doesn't really matter. And then we calculate a corresponding distribution of eta and then compare with beta with some metrics. We also bootstrap the process to account for the error bar on the measurement. And then this gives a distribution of the best fit thermal inertia. And so this gives also a solution that depends on the roughness that has been injected. But again, you see that in all cases, you have very low thermal inertia. And so the best fit is obtained for a value of 2.5. And this is the way you presented it. So the black points here are the measurement. And a value of 2.5 correctly reproduces the increase of the beaming factor with heliocentric distance, while it would be overproduced by a larger value of the thermal inertia. We can also do the same exercise by splitting the data in bins of heliocentric distance. And if we do that, we see a trend for a decrease of the thermal inertia with heliocentric distance, as you see here on the right panel. Now, if we go back to the beaming factor as a function of albedo, the interpretation is that high albedo objects have even lower, particularly low thermal inertia values. And to fit this trend, we need, in fact, to invoke thermal inertia less than 1 for the high albedo objects. So, in summary, for the thermal properties, we find very low surface thermal inertia, and we're much lower by orders of magnitude at compact ICs, also lower than other IC bodies like Saturn satellite, Pluto, or Chiron. The comparison with the other IC body, in fact, indicates possibly an effect related to the different period of rotation, because TNOs are fast rotating objects, and therefore the skin depth that's measured is shallower than in these other icy satellite bodies which have a longer rotation period. So this could suggest that the thermal inertia increases with depth, as has been suggested in other contexts. Now, this very low thermal inertia compared to the value for compact ices indicates a porous upper surface with important heat transfer by radiation in pores. I would like to mention also that, so Pete reported this value of the thermal inertia at the comet of about 20. It is almost an order of magnitude higher than what we get, but if you account for the difference in temperature or in heliocentric distance, and okay, there are different ways to rescale it with temperature depending on the regime for heat conduction. But for example, if you rescale it by T to the square as is expected for radiative heat transport, then you would get at the distance of rescaling the comet value to the distance of TNO, you will get a value that's consistent with what is measured. So in fact, the vastly different thermal inertia at the comet distance and at the TNO distance might in fact just reflect the difference in temperature with perhaps the same physical mechanism for heat transport. It's not contradictory. Okay, I would like to finish by mentioning a study that's in progress. Now it's in a paper that's submitted by Csaba Kiss, and the work has been done, in fact, essentially by Csaba and by Thomas Müller. And it's on the new ideas on how to combine thermal measurement with occultations. Because stellar occultations have the reputation to provide extremely accurate values for the diameter. But in fact, it's not necessarily true, because this is true only if we know the shape very well. Otherwise, if we have only a limited number of chords, then you cannot distinguish the oblateness of the object, and therefore the equivalent diameter is uncertain. And the example is here on the case of Eris. Eris was observed. This is in a paper by Sicardi et al. In Nature, and there were only 2 chords. And with 2 chords, you can fit a very accurate circular orbit. It gives you a good fit with a radius uncertainty of only 6 kilometers, which is great. But actually, the shape is unknown. And if you assume you could have an elliptical shape, you could also fit the object with a very different effective radius. So what they did in this paper was explore the range of solutions for different assumed orientation of the ellipse, and you find that there is a very large, actually, uncertainty on the effective diameter as measured from the occultation, like plus or minus 90 kilometers. Of course, each of these solutions, in terms of the effective radius, is associated with an apparent oblateness. Now, the apparent oblateness results from the true oblateness and from the viewing angle. Yes? And also, for an object that's big enough to be presumably in hydrostatic equilibrium and assumes a Mach-Lorentz shape, the true oblateness is related to the rotation period, which itself is unknown. So in fact, the occultation actually defines a range of solution in a parameter space that includes semi-major axis, rotation period, and viewing geometry. And this is summarized here in this particular case of Eris. Here, theta is the viewing angle with 0 for pole on, and A is the semi-major axis of Eris, and you have all this range here which actually fits the solution. And you can view it also as curves of equilibrium for different rotation periods. So you have all this family of solutions that fit the occultation data. Great. And now what you can do is that you can do a thermal model with all of this parameter space and compare it with your thermal data and see if it helps. And for Eris, it helps a bit, but there is a further complication. Eris has a satellite, Dysnomia, and Dysnomia is darker than Eris, possibly much darker, and possibly not much, much smaller. So it's likely that Dysnomia contribute to the thermal flux. So it complicates yet more the problem. But even though they found, and this is submitted, is that first they found that Eris Dysnomia has to contribute to the flux, otherwise you get a poor fit of the spectral energy distribution. Here the red models are the Eris only model, and while the black models include Dysnomia, so the fit is better with Dysnomia. So for Dysnomia, they use the simple NITM. I'm done. And even if you include dysnomia, then you are able to somehow reduce the parameter space. So this study is not completely discriminatory, but it gives maybe a new idea on how to combine thermal data and occultation measurements with all the physics that's behind it. And this could be, for example, the possible temperature distribution in the Eris dysnomia system. So I'm done. Here is just the summary. I will not read it. Just mention at the end that now all the results are public, and you can find the observing condition, the fluxes, and the radiometric solution under this web page. So thanks.
Thank you. Time for one quick question. Oh, okay, so.
Can you go to the color albedo plot of the different groups? Right. This one. I should say that you have those in more unstable orbits. You have these gray dark objects that are very similar in color and albedo than comets.
Yes.
There is a paper by Melita and myself showing that in the case of the centaurs, the objects in this region are those that likely have a closer perihelion, that had a higher possibility to have been comets in the past.
Yes. Okay.
Right. So I should say that I should say that you cannot discard the hypothesis that you have maybe both effects, or at least both effects.
Okay.
Some objects that were comets in the past has their dust mantle, that it is very dark and it's not very red like the others. The slope is usually lower than 10%.
Okay.
Right.
Right.
The methanol, I'm not very happy. We don't see many methanol in this.
No, you don't have to see methanol.
Yes, I understand.
Methanol
It's the radiation of methanol.
Flatless red color object.
Yes, but I understand that if you irradiate methanol, that you produce this.
Yes.
But
that's the advantage of the model. It cannot be disproved because it claims that
what
methanol has
I see
disappeared.
there is those objects that never has zero chance to be comets. None of them is comet.
Yes. Okay.
Very, very quick. Can you tell? I didn't get where is supposed to be the methanol line?
Well,
What's the eccentric distance? I didn't read this paper.
it's here. It depends also on the size of the object, but typically it's here, 28 for small objects. Then, of course, for large objects, you can be closer because you can retain gravitationally the escaping gases. So there is a correlation with diameter. But if you think of the small size object, it's
No, but in the nebula,
Yeah.
Below 20.
about 28. You put methanol here, 28.
Okay, great.
Yeah.
Thank you. So the next talk is Santos Sands on thermal light curves or trans-Neptunian objects with Herschel-PACS.
Sí, el rojito apunta. No, eso no. Solo para apuntar. Se me mueve con... un poquito para atrás. And look at my nails.
Okay, thank you. So we continue with trans-Neptunian object with Herschel Space Observatory observation. Now I go to present some thermal light curve observed with Herschel-PACS. What we can get from this thermal light curve? First, if the thermal light curve is correlated with the optical, the variability of the body is mainly due to the shape of the body. If it's anti-correlated, this means that the variability is due to albedo, mainly to albedo marks. Of course, a situation between the two limits could be the most plausible for most of the bodies. Some important thing is that if we have this thermal data, this light curve, thermal light curve, we can apply thermophysical model, but we need, as Emmanuel said, we need more information on the object that usually is not available for trans-Neptunian object or for centaurs. In some case, we can have this information. In other case, we should assume a model, we should assume a shape, a rotational period. Usually we can have this rotational period, and spin axis is really very difficult to derive. In this case, then we can get the thermal inertia. We can get, if we apply this thermophysical model, the surface roughness. Oh, I think I have a problem with the font because okay, the G and the okay. You can see here a simulation of the thermal distribution in the Haumea surface, derived using the thermal light curve with Herschel-PACS and using a thermophysical model. Also, in particular, we can constrain, we can derive the thermal inertia from the amplitude of the thermal light curve, and also, if we can measure a delay between thermal and optical light curve, we can constrain, using a thermophysical model, the thermal inertia. Okay, very quick. PACS is the photo detector array camera that is in Herschel Space Observatory, and it has three bands at 70, 100, and 160 microns. We call this band the blue, green, and red band. And the important thing is that these wavelengths are near the maximum thermal emission of TNOs and centaurs. So we can detect the thermal emission of these bodies, of this icy body, with this instrument. PACS has two observing modes. One is choke node, the other is scan map. We use, in fact, mini scan map mode to the observation of TNOs and centaurs with Herschel. This is an example of observation in the green band at 100 microns. At the left panel, you can see, okay, the red circle is Makemake itself, and you see that the background is contaminated. We use follow-on images to build a super sky, and we subtract this super sky in order to clean the image and to perform the photometry in a clear image. This is for the green band, for instance, for Makemake. And this is for the red at 160 micron. Usually for the larger wavelengths, in this case at 160 micron, the background is more confused. So this technique is really very important to extract good fluxes. We observe eight objects. We observe thermal light curve of 8 objects. I think 7 TNOs, 7 trans-Neptunian objects, and one centaur. We have 4 thermal light curve clear detected for Haumea, Varuna, Pluto, and 2003 VS2. Three of these objects have been observed within the GNO Circle project. Pluto was observed within the Open Time 2. We have three light curves that are only marginally detected for Quaoar, Chiron, and Eris, observed in Open Time 1, and Chiron in mass-do observation. And there is the last light curve for 2003 Z84 that is not detected. So we start with the thermal light curve clearly detected. The first is Haumea. Okay, this is a quick portrait of this object. One of the important things is that Haumea has, where is the pointer? Okay, Haumea has an asymmetric light curve with a large amplitude, 0.28 magnitude. This asymmetric light curve that you can see here is telling us that is informed us that there is a dark spot in the Haumea surface that decreases this flux in this case. So, okay, this is less bright in the optical light curve, but one expects in the thermal, as is the dark spot, that the fluxes should increase in the thermal light curve. Okay, I think this is the more important for the next. Haumea was observed in miniscan map mode at 100-160 microns in December 2009 and also June 2010. And we face the thermal observation using a very accurate rotational period that you can see here. Here is the result of applying a simple standard thermal model. Also using in this case, we use the mean fluxes from the light curve at 100-160 micron. And also we use the Spire observation and the Spitzer data. We can derive the diameter, albedo, and eta. And the light curve itself is this one. This is the Haumea light curve of 100 micron. The first thing that we see is that the field curve is the optical light curve, and we can see that the optical is correlated with the thermal. So the light curve, the variability is primarily due to the shape of the object. The dotted line is the optical light curve, but rescale with the thermal amplitude. So we have, in fact, that the thermal amplitude is 1.72 times the optical amplitude. Here is the region where is expected this dark spot region, and in fact we can see that the flux is bit larger compared. There is an increase in the flux compared with the other maximum here. So we think we are in fact detecting this dark spot. Okay, if we apply a thermophysical model, in this case we can, because if we assume a shape model, also we assume an aspect angle of 90 degrees. And this is a thermophysical model, but without a spot. We don't consider the effect of this dark spot. And we explore different but small thermal inertia from 0 to 0.5, and also different phase angles. We assume no roughness, so eta here is equal to 1. We see here that a dark spot, to model a dark spot, is needed to reproduce this part of the thermal light curve. So if we include a spot model, and spot covering 1/4 of the Haumea maximum projected cross section, as suggested in Lacerda et al. 2008, we can reproduce this increase in the fluxes. In this case, I can't see here, but I think here we fix the thermal inertia and we explore different phase integrals. And here we fix the phase integral and explore different thermal inertia values. The best fit here is the red line, and here also the red line. Are not perfect fit, but more or less consistent with what we expect for the darkest. This is the Haumea light curve at 160. Here we don't detect this dark spot in this case, and the amplitude of the thermal is a bit smaller. Okay, this is the best to fit that we get from the 100 micron applied to the 160 micron. These are all preliminary results that, of course, we can play a bit more with the Q in order to better fit this thermal light curve at 160 micron. The conclusion for the Haumea light curve is that the darkest spot is needed to reproduce the observed light curve. We get extremely small thermal inertia, less than 0.5, and probably less than 0.2. Q should be high, at least 0.8 for thermal inertia equal to 0.1, and it should be even higher if surface roughness is important. So a small change in surface properties, dark spot, affect significantly the emitted flux, and larger changes are excluded by the data. The most plausible scenario invokes a slightly higher thermal inertia in the dark spot compared with its surrounding. Okay, a quick portrait for other light curve clearly detected, that is Varuna. The more important thing here is that it has a large visual amplitude, 0.4, a moderate albedo, and we observed it with Herschel at 100-160 micron in April 2011. Here you can see an animation with the Herschel images at 100 microns, where you can see how the Haumea change, flux of Haumea change is really very clear in the animation. This is what we get. Again, the thermal light curve and the optical are correlated, so we can say that the variability is primarily due to the shape. Now the optical amplitude, the thermal amplitude is 3 times, the amplitude of the thermal light curve is 3 times larger than the amplitude of the optical. And also we have, and we measure a delay between the thermal and optical light curve, and we get around 13 minutes of delay. So, okay, we have also here this weird thing that maybe are some albedo marks, or could be also a contamination of the background. This is the same, the Varuna thermal light curve, but at 160 micron is noisier. And here in this minimum, we haven't this weird pattern that we have in the 100 microns. Okay, if we assume a shape model, we can also apply a thermophysical model. This is the best result, but 100 micron. The same for 160 micron. And we can get from the amplitude, as I told, a constraint for the thermal inertia. The best thermal inertia compatible with the 100 microns, like with the 100 thermal amplitude, is around 1 in SI units. And the same we get for the 160 microns light curve. We also can constrain the thermal inertia using this delay. We get that for a delay between the thermal and the optical light curve around 13 minutes. We have a thermal inertia again close to 1. For 160 micron, this doesn't work because we get, in fact, a larger delay. So probably because the 160 micron is noisier than the 100. So summarizing the result, the amplitude of the light curve at 100 and 160 constrain the thermal inertia equal around 1. From the delay time, also we can constrain the thermal inertia. There is an increasing flux near one of the minimum of the 100 micron light curve, maybe due to albedo variations or contamination background by a background source. We think that is due to contamination because if we plot here, this is the Varuna background. Okay, the field when Varuna was at 100 micron. When we did the two observations with this is the first, this is the second. Clearly, during the first part of the observation, the first day we observed, there is a source really very close to the position where Varuna was at this time. So even if we apply this sky subtraction, it's not possible to subtract everything. So probably this strands or weird pattern we see in this minimum is due to this background. Okay, Pluto, the Pluto light curve is also detected. We detect this light curve at the 3-PACS wavelength, 70, 100, 160, and also till 500 microns because we observe Pluto with Spire also. You can see here the light curve from 70 microns to 500. So the decrease of brightness temperature with the increase of the wavelength is observed beyond 100 microns. It was previously observed with other measurement with a Spitzer, and the Pluto fading over 2004 and 2007 is not confirmed in our measurement. Okay, the last clearly detected light curve is for 2003 VS2. It's a Plutino with no satellites, and we have an optical amplitude. The amplitude of optical light curve is 0.2. So one expect to detect in the thermal data the light curve. We observe in this case at 70 and 160 microns. If we face the thermal data, this is what we get. Okay. We start to model, in this case applying a thermal model. We use eta values close to the eta value that we derive from the NITAM, because apart from this light curve, we have another observation, and we can derive, we can apply this NITAM or STM, and we obtain eta equal to 1.57, I think so. So we try with this different eta. The best fit in this case is for eta equal 1.5. That is the red line. Of course, here we assume we need to assume if we want also to apply a thermophysical model, and it is not the case, but we need to assume a shape model. This same model was derived from the thermal equivalent diameter and from the optical light curve. Okay, it's just approximate shape model. But the good news is that we have multi-core stellar occultation from November 2004 14, I think we have 4 cores. So we can, for sure, we are prepared now to derive a best shape model, and then maybe we can apply a thermophysical model and get more thermal and physical information from this light curve. Okay, this is at 160 micron. That is really very noisy. These are the marginally detected light curve. This is for Quaoar. You can see, okay, the amplitude is really very, very small. But if we phase with the optical light curve, looks like that the thermal light curve is there at 100 microns. We have also observation of the centaur Chiron at 70 and 160 micron. Maybe this centaur is as well the second discovered ringed object, ringed minor body in the solar system. If we face this data using the rotational period by Martialis and Buratti, we have this. Okay, it's difficult to say if we have the light curve here, but maybe this needs more work. For Eris, we also have a partial or incomplete detection of the light curve at 160 micron. The problem is that, as Emmanuel pointed out, there is no very reliable rotational period. Okay, the most reliable are around 14 and 27 hours. So it's also difficult to say. And even we only have some, we only have a part of the possible thermal light curve. And this is the last 2003-84 that is a non-detected light curve. If we face the data and we plot the optical, is very difficult. Also try to use another method in order to detect, but I think this is not detected, probably due to the small small amplitude of the optical light curve. You see, it's only 0.1 magnitude. And as general conclusion, we have many thermal measurements which will allow us to constrain size, albedo shape, and thermal properties. This applies to the thermal light curve via thermophysical model, but optical light curve that we have, in fact, are needed, and also occultations to derive size shapes that can help to properly apply this thermophysical model. So we need this definitively occultation information for best interpret this thermal light curve. And that's all, I think, on time. Yes. So thank you.
It's actually just a general comment. If you derive thermal inertias, we have seen some very small values now for TNOs and so on. It would be helpful always to give, in brackets, the temperature range underlying the observations, because especially at low temperatures, thermal inertia depends very strongly on temperature. So this is an important information to compare it with material properties, with models of what the surface is composed of, and so on.
Okay. Okay, yes. Javier?
Pablo, nice talk. I wonder if your optical light curves are close enough in time respect to the thermal ones to be so sure about the co-phasing of both.
Yes, I close enough, and in fact we have a small uncertainty in the phase when we do this when we phase with this rotational period our thermal observation. So yes,
Very close.
yes, or very close or very accurate.
When you propagate
Yes, this.
Haumea, for example, the
Oh, yeah.
rotation period is known with 5 or 6 significant digits. You can extrapolate for 1 year.
But only on.
Yeah, but these are typically the objects we have. They are well
Yes,
characterized.
yes. Okay, no for Eris because we don't know what's the rotational period, but for the others we have accurate rotational period. And maybe I forget to say this at the beginning of the talk that yes, for Haumea, but for the others maybe it's not was not so clear when I explained. Okay. Thank you.
The same. Just to be sure that I don't steal it.
So the next speaker and last speaker of this session is Tanga. Yes, good. Who's going to tell us about the contribution of Gaia to solar system science.
Okay, thank you very much. So, of course, the Gaia is not observing anything in thermal infrared, but I think Marco encouraged me to give a talk just to show which kind of data we will get from this mission, which is quite unique, and how they will impact activities in general for solar system studies, even for thermophysical modeling, because this is related to determination of shape, rotational periods, etc., that are of interest to you. So let me, I don't know if everybody here is familiar with Gaia, so let me give a very short introduction to the subject. Gaia you can see Gaia written in several different ways. Only one of those is the correct one. You can try to Google to find what is Gaia for Google, and you fall on something derived from the Greek name of the Earth, of course, some esoteric pictures, then you find wines, then you find tattoos, then you find other logos of wines, other exotic things, even a variety of Nutella, and then if you are lucky, you find the Gaia in the Google Images set. So the name of Gaia, in fact, originally was an acronym as Global Astrometric Interferometer for Astrophysics. Then this was a concept, a preliminary concept for the mission, which was abandoned. So exit the interferometry from the mission, but the name remained written like a person name, which is the first capital letter. And this is no longer an acronym; it's just a name as a person. It's a kind of a strange choice, but that's the way it should be written and interpreted. Okay, so what is Gaia, in fact? Gaia is a European mission, a cornerstone mission of ESA, planned to observe the sky over 5 years. It started in July 2014. It is a trajectory around the L2 Lagrangian point of the Earth, external to the Earth orbit, where it describes the Lissajous trajectory, avoiding the central region, which is eclipsed by the presence of the Earth's shadow for over 6 years. And okay, it has an equipment suited to perform radial velocity spectrophotometry, but mainly its main strength is astrometry. So it will observe all the stars down to magnitude 20, so basically complete in magnitude, because the selection of the targets occurs on board. There are no input catalog for the mission. And the target accuracy is 25 microseconds in the positions at magnitude 15, which degrades at around 200 microseconds at magnitude 20. Of course, it's a function of magnitude. So now this was the nominal target. The target after commission of the mission is a little bit deteriorated related to these figures. We can assume a 30 mass at this level. Deterioration factor is a little bit higher for magnitude 20, but still these are very impressive numbers compared to current stellar accuracy. Also because this is global astrometry, so there are no zonal errors in the outcome. So it's a completely scientific mission of ESA. Going fast, so which are the strands? The strands, the instruments cover different needs, so from the astrometry to the physical characterization of the targets, uniform sky coverage, about 80 observations per each position on the sky. It's a self-calibrated instrument because on board there is all the telemetry needed to monitor very carefully the geometry and the stability of the system, and it is supported by a very motivated community. In part, it was working already on Hipparcos, the previous European astrometric mission. So this is the section where the payload is, and this is the plot showing the enormous improvement in astrometry over history, starting from Hipparcos, 150 BC, and then going down to the epoch of CCDs, and then going to space, let's say, from here, from FK5 to Hipparcos, with a gain of 2 orders of magnitude in accuracy from positions, and then Gaia, another giant leap toward much higher accuracy. So there is really a transition here due to going to space the first time and employing better technology the second jump. Okay, so Gaia, if you explode the Gaia, it looks like that. Here are the optics of Gaia, two telescopes, basically 2 square mirrors, looking at 2 directions, which are separated by the so-called base angle, 106.5 degrees apart. And all the structures rotate rigidly around the rotation axis with a speed of 6 hours, period of 6 hours. And the focal plane common to both field of view is here. It's a huge array of CCDs, 106 CCDs, equivalent to 1 gigapixel. The physical size here is about 0.5 meter times 1 meter. So it's a digital camera this big, with the biggest focal plane ever built, ever flown in space for sure. Now, Pan-STARRS focal plane are the same order of size now on the Earth. So there are several CCDs, and what happens is that due to the fact that this satellite is rotating continuously, it executes a scanning motion on the sky along great circles, and the image of a star falling on the focal plane drifts following the rotation of the satellite, of course. So our star will visit the different instruments here will be detected, and then it will be followed on these blue-gray CCDs, which constitute the astrometric field, where the flux arrives basically unfiltered on the CCDs, and it passes in front of these 2 columns, which are the blue and red spectrophotometers. Basically, these CCDs have dispersing elements in front to provide low-resolution spectra. And then this last instrument encountered is the radial velocity spectrometer. It targets a small range, the wavelengths at high resolution, to get radial velocities and chemical abundances for stars down to magnitude 17. So this last instrument is rather limited in depth. Okay, so how it works? Well, of course, it spins. Now, to cover the whole sky, you have to combine different rotational motions. So the first one is the spin. The second one is a precession of the spin axis around with on a precession cone, which is centered in the direction of the sun. And the third movement, the rotation of the whole complex around the sun over 1 year. So basically, over 4 days, you get nearly overlapped paths that slowly drifts. And over a longer time scale, you get a more complex motion which covers the whole celestial sphere. So nice movie here, if I can start it. Fingers crossed. Yes. So this is the ecliptic plane, the whole sky represented. At the beginning, the Gaia spin axis, we suppose it is there, 45 degrees away from the sun. And with the passing time, hours, you see the regions that Gaia is scanning. The color represents the density of the number of scans, okay? So now the precession is slowly drifting the circle. If we accelerate the process, the precession around the direction of the sun that is moving here accelerates, and you can see how these circles cover the sky. And then we go even faster, and we see that over 5 years, we get a very nice pattern, very carefully optimized. And in fact, okay, so due to the fact that you have two different viewing directions on the same focal plane, what you are doing is simply to bring an angular measurement from two distant portions of the sky to reduce it to a measurement of a small distance on the focal plane, which is much more precise than measuring large angles. So this is the principle, the basic principle of Gaia for high accuracy, and the principle that allows to eliminate the zonal errors, because you observe regions on the sky that are very distant apart. All the system, and then all the observations are given to a processing system that will solve the global astrometric solution of the celestial sphere, including calibration parameters and instrumental parameters. So a big inversion problem. Okay, now Gaia is real, not only simulation. So this is the focal plane I was showing before when it was being assembled by the industry. So these are the guys assembling the focal plane around the electronics. This is the bigger silicon carbide torus supporting the optics. Here are the engineers with trembling hands that are fixing the mirrors. And this torus is in fact a single piece of silicon carbide that was raised in a oven that was built explicitly only for this building one piece of for Gaia. And it's the biggest piece ever built with this technique. And okay, this is during testing in the labs. This is test of sunshield deployment, October 2011. Then the sunshield was separated from the central part, the payload, and they were shipped separately to Kourou, where they were assembled and retested and then launched on December 19, 2013. So travel to L2 followed, commissioning followed, and then Gaia is operating since July 2014 now, transmitting to the ground about between 50 and 100 million observations per day, meaning essentially single source observations per day. Depending upon the density that Gaia is scanning on a single day, you can have higher density or lower density. If you're scanning, for example, the core of the galaxy, you peak to more than 150 million observations per day. Okay, so at present, data processing on the ground is running daily, being improved also. So astrometric performances, daily performances are nominal. What you get from a single detection without any calibration is an accuracy of about 70 milliarc seconds, which is pretty good relative to what we have available today already. And of course, if you average different positions already without doing much effort, you get much better accuracy. Photometric performance are also good. There is a slight degradation due to in the background that is higher than expected, and some contamination due to contaminants that condensate on some mirrors that periodically need some decontamination maneuvers. But this is not a big issue, it seems. And the astrometric global iterative solution is this big computer code is being trained now on the real observations, and will be ready to deliver data for first data release that is foreseen next year. So you find on the Gaia website several nice examples of performances. I just invite you to browse through them. Here is one of the first examples showing the single-day astrometry. So each dark point here is an astrometric measurement by Gaia. The typical dispersion is those 70 milliseconds I mentioned, just because there are no specific calibration, there are uncertainties on the attitude of the probe, and that will be completely removed by the global iterative solution. But here at this level, you can see the astrometry, in this case, of the gravitational lenses. This is the Einstein cross. It was released on the day recently for the anniversary of Einstein and this was the gift by Gaia. You see here the central component is detected there. It's too faint, so it is not detected. But the image on the background, of course, is not Gaia. It's HST, and it shows that things are going pretty well. Okay, so coming back to solar system now, what Gaia will do for solar system? Of course, it detects everything down to magnitude 20, so we can consider it will observe about 350,000 asteroids, meaning this is one south every 2,500 observed by Gaia. So we can count one south every 2,500 stars. Most of these asteroids will be already known, in fact, most of them, because we are nearly complete down to magnitude 20, apparent magnitude 20. We'll not observe large bodies. Basically, very extended objects are not being selected on board, so observation are not being obtained. This includes large planets, large planetary satellites such as the Galilean satellites. Okay, and about these constraints I already mentioned. So between magnitude 6 and 20, sites about smaller than 600 milliseconds, 70 observations per object, but with large fluctuation, there are many asteroids that are observed maybe 200 or 250 times during the mission, simply because the geometry is particularly favorable for them. So when the scanning motion of Gaia crosses the ecliptic, if you look from above the ecliptic, you can simplify a little bit the appearance of the scanning law, and you will see that there are two regions that the Gaia is not pointing toward the sun, of course, and also toward the opposition, which is the usual direction from where you observe asteroids from the Earth, especially in the main belt. So Gaia, on average, observes at quadrature with respect to the Earth. So this is the expected final accuracy on a single observation. So I mentioned 70 milliseconds for a single observation today without any calibration. But when you will be able at the end of the mission to reduce with respect to the global astrometric solution, to eliminate the component linked to the attitude, uncertainties, etc., you will go down to these figures here for a single date. So magnitude 15, you will be around 0.1 millisecond, 1 millisecond in magnitude 20, which is really impressive. Just to have an idea of how this relates to for example, to the size of the object, you can, if you just take the typical photocenter shift due to shape effects of very regular asteroids, can be up to about 10% at large phase angles. For a typical object of 15% albedo, at 2 AU or 3 AU, you get these two lines representing the amplitude of the photocenter shift. So meaning that basically for large objects that are in these magnitude ranges here, in this region, you can detect, in fact, a photocenter shift related to the wobbling due to shape effects. So you have to take into account several subtleties when reducing astrometry of asteroids. And of course, this is also a capability of detection of these subtle effects. Something went wrong. Oh, PowerPoint is needs to close. This never happened before. Well, okay, let's try. Just don't look at this very exciting scientific result it's preparing here. Coming back. So. Okay, we're here. Good. Okay, so you can translate the detection capabilities in magnitude to magnitude 20 in a detection capability based on diameter as a function of the heliocentric distance. So you can see, for example, that Gaia will observe main belt asteroids between 2-3 kilometers in the inner belt and 10 kilometers in the outer belt. You can go down to about 1 kilometer for the air crossers, of course. Let's say that at these limits, Gaia is not a big machine for discovery, okay? Even if, of course, completeness is not certainly 100%. So some new objects are expected to be detected. And in the Kuiper belt region, you will just detect very large members, a few. So photometric accuracy, just for a single transit again, just look at the black curve concerning the astrometric field. You are at about 1/100th of a magnitude at magnitude 19. So again, with such an accuracy, you can do many things related to the shape of the asteroids by studying the variability. Even if it is a sparse photometry, it can nicely complement ground-based light curves. And we know that now by using sparse photometry, we are able to retrieve at least ellipsoidal shapes and periods. Alberto, who is here, is responsible for this part of the processing. Wow, that's incredible. I think I will take the PDF version if I can. Just let me look for it. That's very unfortunate. I take the PDF, and this way I get rid of Microsoft stuff. Enter full screen. Okay. Okay, sorry. It's coming. Okay. So this is a PDF. Safe format. Okay, so the low resolution spectroscopy, how it works? Well, I mentioned these two CDs with a dispersing element, two prisms in front. Here you have the blue part and the red part of the spectrum for different spectra type of stars. And in fact, what you get for the red and the blue part is I would say a dispersion which varies with wavelength, corresponding to about 25 independent bands for each of the two domains. So pretty much to do an accurate taxonomical classification. If you compare the Gaia wavelength range with the SMAS, for example, wavelength range, you see that Gaia pushes the limit further to the blue, where you can disentangle between some strange spectral types. The blue part, it is essentially missed in the recent classification, so you can do many things here. Now, below 400 nanometers, sensitivity drops quite quickly, so this then depends upon the brightness of the target, what you can really do. But if you heavily beam this part, for sure you can have enough signal to say many things. Okay, so behind Gaia, there is this community of scientists that are part of the Data Processing and Analysis Consortium. They are in charge of calibrating the observations and also of extracting the scientific information for the benefit of the community. When the data are published, basically, there will be also these data products that will be available with the Gaia observations. So by the end of the mission, for concerning asteroids, we will have these products coming from astrometry, CCD signal, spectrophotometry. So I already mentioned the astrometry, which will produce about two order of magnitude improvement in the certainty of asteroid orbits. There will be relativity tests performed by using the precession of a perihelion for several minor planets. Masses from close encounters, maybe 100 is a little bit optimistic. Let's say 60 from Gaia observations only, but 10% accuracy. So the 60 heaviest perturbers in the belt, which is a very good number compared to the current knowledge of asteroid masses. Some direct diameters of asteroids and binary asteroids detected as separate cells above 120 mass. Spectrophotometric data and light curves, as I mentioned, providing compositional constraints and parameters related to rotation and shape. Okay, so basically this is what we expect in the global picture with the numbers above, orbit improvement, shape and pose and taxonomy for about the whole sample. Binary, we don't know exactly how many of them. The weakness of Gaia is basically in size and mass determination. But of course, there are a lot of science that can be done by combining parts of this data with, among them and with other complementary data coming from the ground. For example, size is coming from WISE or from polarimetry or other. Okay, to reach this goal, the processing consortium has implemented 2 pipelines, one for the daily processing, basically for asteroid alerts when an asteroid is discovered, and the other one, long-term processing to produce the data release for the mission. So I'm in charge for the coordination of the activity of this group dealing with this data treatment. Now, let me just conclude very quickly with a couple of examples showing the strength of Gaia. Here you have an example taken by this publication, the Maretal 2013, showing the uncertainty, the position of the asteroid Apophis, one of those dangerous guys, and the uncertainty following the currently available data set basically is given by the black line and is represented as a function of time as a position uncertainty on the distance of Apophis from the Earth. Okay, you have some periodicities due to the fact that you have close encounters with the Earth and variation in distance, etc. But basically what you have here is the result of about 1,000 optical observations plus several other astrometric determinations. Now, if you just add a single Gaia data point, this uncertainty collapses to the red curve here. And if you add all the Gaia observations, you basically don't see any fluctuation at this scale, simply because you reduce really the uncertainty of a factor of 100. Okay, so this, of course, is the result of simulations. Now, you can imagine to play the same trick in the past and use, for example, past astrometry of asteroids and reduce it by using the Gaia Stellar Catalog, which provide an enormous amount of astrometric reference stars for any field that you have in your archives. Just going on any image, pick up the stars, and you will be sure that you will plenty of Gaia stars down to magnitude 20, and you will be able to reduce the astrometry. So, of course, it has about the same impact. The more you go in the past, the better you can improve the orbit of your objects and maybe detect subtle effects such as the Yarkovsky drift. And here the example is again on Apophis, and here is a close encounter of the Earth in 2030. But the main difference here is done by the black curve with the current observations. And if you re-reduce the same observations using Gaia astrometry, you get the lower curves, color curves, different colors depending upon how many observations you re-reduce. But basically, again, you find these 2 orders of magnitude improvement, which I was mentioning. Okay, so this is a very rewarding activity, but of course an enormous task if you want to do that systematically. I don't think the community is really prepared in general for doing that on a systematic basis on all the targets we have. Another impact Gaia will have will change basically the approach to some observational activities, for example, stellar occultations. But now you have to, in several situations, you have to pack your bags and your telescope and drop it on a plane and fly somewhere to chase the shadow path of an asteroid. Now, the point is that with such an orbit improvement and with all the astrometry of the stars, even much fainter stars, for which we will have an accurate position than now, you will be able to have a very accurate predictions, and basically you will reduce the uncertainty to about 10 kilometers on the position of an asteroid. So you will be able not only to say where exactly the occultational course, but in which part of the occultation path you are staying with your telescope when you consider an asteroid which is maybe 50 kilometers in size. Okay, so let's imagine a network of some robotic telescopes performing this task systematically. down with stars down to magnitude 15, maybe a couple of 1-meter telescopes. They will have tens of events per night to observe each night, and to sample systematically all the asteroid belt and make all side sensors that you can imagine. Of course, there are problems behind, as also Emmanuel showed, when you just a small number of cores, but still it's incredible power behind this exploitation of Gaia data. So when these exciting results will come, mid-2016, the first intermediate data releases covering about 90% of the sources. Of course, positions will be graded relative to the last release, which is foreseen for 2020, but still, you will have typically positions of degraded by a factor 3-4, probably, not much more than that. Well, I won't go into many details here, but we are working for having solar system objects also in the release, maybe not all of them, maybe just a subsample of 10 to the 4 asteroids, maybe those larger than 10 kilometers. Astrometry of objects that are rarely observed, such as TNOs, very useful to predict future occultations. So be ready to exploit the Gaia data soon. And to be ready, just finish with an advertisement. There is a postdoc position in Nice for 2 years. If somebody knows, good student that want to apply to work on Gaia and on the forthcoming releases, please get in touch with me. It's not such a bad place to go. You can show this picture to whoever is interested. Okay, thank you.
Any questions?
You mentioned the constraints on solar system objects for Gaia, like not too bright, not too dark, not too big. But what about if you're talking about binaries, like binary asteroids with a very big primary, a small secondary, which is close by? And I'm also interested in comets. So if a comet has a coma, does it somehow spoil the measurements, or does it make it impossible?
So we tested the capabilities of detection of point stars embedded in a diffuse luminosity, such as a nucleus with a coma. As far as you have a peak in the central part of the coma, it can work pretty well. The problem is when you have no peaks, you have a very flat coma. In that case, efficiency detection falls very quickly. But concerning binaries, among satellites, among binaries, among asteroid satellites, we have situations in which satellites are separated by more than half a second. So this is not a problem. Separation is not a problem in that case. But the secondary must be brighter than magnitude 20, of course. So this is the main constraint. And turning the separation, you get them as 2 separate sources when they are separated by at least 360 milliseconds. If they are closer, then you will have to analyze more closely the signal around each source. There is nobody for at this moment foreseeing this job, but it's something that can be done when the Gaia data will be released, in fact.
Any other questions? Okay, I've got a quick one. How do you see the things like the Gaia data set fitting in with other big ground-based surveys like, the LSST and things like that are coming online?
Well, there is a nice complementarity between Gaia and LSST. Basically, LSST starts when Gaia finishes. And the LSST community is very interesting to have a precise astrometric reference, because they will observe a much smaller field. So having a good astrometry of Gaia will strongly help them. Then they will, of course, they will go much deeper, much fainter in magnitude. So there is a nice complementarity. Concerning solar system, I think that I have to mention certainly size determination. I mentioned it as a weakness for Gaia. We have Akari, we have WISE, which are very complementary in that sense. And WISE has about the same order of magnitudes in terms of number of objects. So I see a very nice match in those figures there.
Thank you. Okay, in that case, I'd like to thank all our speakers again.
Thank you.
then it's this open. There's a round table or open discussion. So I'll hand over to Javier. Yes.
Okay, it's Marco. Where's Marco?
Yes, sir.
Oh, yes. You are the boss.
No,
Yes, yes, you are.
don't have the thingy. Paolo?
There you are.
Ah. Well, I just wrote down a couple of things, not much, honestly. That I took notes. Well, yeah, that I took notes. So the first thing is what's temperature? So to me it was, we have a little paragraph in the Asteroids 4 chapter about this, because it's not very clear to everybody what kind of temperature we derive when we use radiometric techniques. And so, for example, I think that what Cedric pointed out this morning, he spoke about effective temperature, but it's more a color temperature. And I think we should be a little careful in defining these terms and so on. And it's one topic we can, maybe I just show what I was thinking about to discuss, and then we can actually discuss if we want. The other thing is to make Alberto Cellino happy. So this is the albedo uncertainty. I apologize if there are typos, because I did it, I prepared during the talk. So that's not good. So this is a paper that just came out in the archive, the Astro-PH. This shows the new H value. This plot shows the H value derived from pan-stars. Admittedly, I didn't read the paper because it just came out. But these are, I know something about this paper. And this HB is the magnitude derived by this survey of 250,000 asteroids, minus the magnitude from the minor planet center, as function of the magnitude from the minor planet center. And you can see that it's like, I mean, there's a random error, but there's also a systematic effect that is quite interesting, because basically at large objects the magnitude are in good agreement, and at the faint end the same, but they don't. There's like a 0.3 magnitude difference in around H14, 15. I remind you that the 0.3 magnitude absolute value corresponded to an albedo relative uncertainty of 30%, just from the H magnitude. Right. Yes. I put that now. If you guys want to add something else, we can do it. I don't know. We don't have much time because we're pretty tired. Then Javier asked me to put this. So missions. Apparently, there's a lack of space mission to solar system bodies. I think it's ESA side, because JAXA and NASA are launching missions. And then Josh and others, maybe we can talk about the problem of the emissivity, especially because when I started dealing with NEATM and these models, the error bars that we got from measurement from the ground were about 5, maybe sometimes 10% when you include the absolute calibration, the atmospheric problem, and so on. But now that we have instruments that fly in space, the accuracy is much better of these measurements. And so we're probably going to be careful here. Cedric wanted to talk about this, I think, a little bit. So and we heard that also from Victor Alilagoa that his TPM does not include this effect. Is it worth including, for example, if we want to calculate DTDT? I mean, the answer is include it and study if it's important. But we can discuss this. And then I was thinking about this, but we can skip it, depending how much time we have. We don't have a survey. Well, Spitzer was not a survey of asteroids, but it did NEO surveys, for example. And then I'm fascinated at what we discussed yesterday on M-type asteroid, and L-type were also interesting. I'm basically reviewing everything, but it's interesting. And finally, this is interesting because to my understanding, but I might have done a mistake, TEORP is spinning up objects. And for detection of YORP over 4 over 4 are positive d omega over dt. So the bodies are all the way accelerating. So how do we spin a small asteroid down? Because we see very slow rotators. That's it for me, and we can start from the beginning if you want. Unless you have other things to add. I'm just moderating it, but just jot down a couple of ideas. First point. Yes. The effective temperature is I think if I'm not mistaken, is the temperature that has the temperature of a black body that oh, I forgot. I forgot. So it's the temperature of the black body that has the same total emission that you receive. The brightness temperature is 1 wavelength. Right, it's like the volumetric temperature. The color temperature is the temperature that a black body, the temperature of the black body that has the same spectrum of the one you receive. So basically, if you fit like a black body, if you have an SCD and you fit a black body, I think a unique black body, that's the T you fit is the color temperature. I never know what's the role of the emissivity in this case. There's no emissivity. It's just it includes it, right? So I think, for example, in the case of Rome, the group of Rome, Federico Tosi actually derives color temperature because he fits the slope of the Planck function in 3 to 5 micron. It also derives the emissivity, but it's a color temperature.
Yeah, the temperature, Marco, it's a quantity in our business that it's hardly to define. And in my talk tomorrow, I will show you some slides, and you will, I hope you accept that it's senseless to define the temperature for a rough surface of an atmosphereless body. This quantity is defined, and many of you are physicists, in a thermal equilibrium. Temperature is a quantity for thermal equilibrium, nothing else. And maybe for the Earth, for the Mars, you can find a region 100 square meters with one temperature, unique temperature. But on a small body without atmosphere and very small activities, you will find 100 square meters. It's like a pixel resolution of any instrument. You will find only regions with big differences in temperature, 100 K and more and more. And this classical picture of thermophysical equilibrium on a scale of a pixel is completely wrong here. That's my problem I have. I've been in this business 30 years now, and I couldn't solve this. It's not a simple thing, and we should think over it, because it can lead to completely wrong conclusions. Let me give you an example. The first data from losses were interpreted in the temperature. Losses in last year had a mixture of 100 square meters, 10 times 10 meters, and you can measure flux, and so you can allocate the flux to temperature. You can do that. The brightest temperature, the average of thousands of different temperatures is in 100K. And it's non-linear average. It's nothing. In physical sense, it's nothing. But what was done, it was that the temperature of this 100 square meters is 230K. It was the first value of losses. This means there is no ice on the surface. It's completely wrong conclusion. Because temperature, average temperature of 230K can be half of the field is 100K, and the other 50% is 300K, can be everything. And that means you can't conclude with such a wrong value that is not well defined, that there's no ice on the surface. And I see a lot of such conclusions and wrong statements, and all these things are connected with this strong definition of the temperature that we don't have. We can do what we want. A single parameter like temperature for such a homogeneous field of 100 square meters or whatever can't be defined in the physical sense, and therefore you can't interpret it. And yeah, I don't have a solution, but I can only say be careful with this quantity.
Yeah, I think it's be careful is the message. So when you write the papers, yeah,
The brightest temperature is nothing more than equivalent for the flux, the division, the quantity and so on. But it has nothing to do with the temperature we need for the thermal models.
Yeah.
Completely different things. And many of us, and including me, we do so because we don't have a better solution. We become unphysical with this statement. And be careful.
The question. Thank you. Well, yeah, I guess I couldn't agree more. We see evidence for this on the moon, where we have lots and lots of high resolution thermal data and multiple different spectral channels with minor. What we see is that every single measurement, even at noon time, when the sun is directly overhead, we still have a mixture of temperatures within the and at the higher latitudes or at grazing sun angles, early morning, late in the afternoon, the temperature gradients are huge. You can get, on the moon, temperature gradients of hundreds of degrees within centimeters. So on these airless bodies, when the regolith is so insulated, you can have thermal gradients of hundreds of degrees within millimeters of centimeters. And when you're averaging, it's not an average, but when you're summing together the thermal emission from many different temperatures within one pixel, the emission spectrum that we get is not a black body. And what we do on the moon is we model this using a thermophysical model is to use the colorimetric temperature. So we measure the thermal emission in multiple different wavelengths. We basically integrate the total flux from all the wavelengths because of conservation of energy. That's equivalent to what your model would be using. That's what I call effective temperature. Yeah. So it's a useful quantity, and then you can match that to your model. But we published a paper on just recently, Josh Banfield was the lead author, describing this small scale roughness effect on the moon and what it does to your thermal measurements and the possibility of small scale cold traps like that. The Banfield and Eris just across the boundaries. Anyway, the point is, we do see evidence for this regardless of the length scale that you're looking at. So you're looking at you were to take the moon and move it out to an asteroid distance to pull this coming together all these facets one pixel. That's a very different template than what you get from the thermometer. You don't need the microphone. Yeah, the microphone only for the broadcasting. Take that home. Yeah, we can take this one home.
This works. Jürgen.
I want to make things even worse. So what you said is absolutely correct, and I can only emphasize the points raised before. It gets even worse when you're dealing with activity, because then you fold your temperature into a thermodynamic function, which is exponential to the -1/t. It's bad if you fold it with t to the power 4, but it's even worse if you get to fold this into an exponential, a thermodynamic function. So it's outgassing rate or vapor pressure, whatever, that goes all with exponential -1/t, and that really is very important, and particularly for cometary surfaces, and those where patches of ice are close to the surface, then it is of utmost importance to be very, very careful here. So another emphasis on that point.
But what do we do now? I mean, we can lament here, and at the next meeting and internally over the years, I mean, I'm sure most of us have come across these discussions again and again. So wouldn't it be nice to write a kind of standardization paper where we put all these definitions together, propose some coherent set of naming and of mathematical definitions to make it very clear? And this could then ideally become the reference paper, so we don't have to repeat it every time we write a paper again, what we actually mean, what we measure, what we are talking about. And ultimately, it could go into IAU resolution, so it could be internationally adopted or something. I think that's Eckhart has had these thoughts the last 30 years. I've been thinking about it the last couple of years. And it doesn't help if you just keep lamenting on this over and over. Somebody has to write a paper, not me.
Let me emphasize again, it's a specific problem of our community, small bodies. And when old guys from Varuna and Viking started to investigate this problem on Mars or also on Earth, we haven't such a problem, because the atmosphere and the other parameters realize a quite homogeneous surface in these scales we have with our pixels from instruments. It's a specific problem of our atmosphereless bodies community, and we haven't solved it so far. And I also have the feeling nobody likes it to forget the temperatures in the future as an outcome of our measurements, because temperature is what you like. And but again, as a physicist, I must say it's simply not defined for such extended surface area, and we have to live with it and must maybe find a way out. One way out could be that we define smaller phases, subpixel on subpixel level, and on smaller phases can mean in this smaller environment we have a thermodynamical equilibrium, can define a temperature. That it's possible, of course, but then you have in one pixel, let's say 1,000 subpixels with a specific temperature for each, can establish Planck functions and can superpose all these things, and can then try to compare this with your measurements. It's also a flux. In principle, you don't need temperatures for this business. But on the other hand, for thermal modeling, you have a temperature in your equations. You can't avoid that, and then you must find a compromise. And or you must perform thermal modeling for each small facet with their own specific temperature for itself, and then come together with hundreds or thousands of such detailed problems. But nobody wants that and likes that. This is it's our specific problem in small bodies.
So basically taking a statistical distribution of slopes and azimuths of all different magnitudes, and then you calculate the thermal model for each one of those facets, and then sum them together statistically, basically assuming a random distribution or whatever you want, and then you can get the thermal emission that you would observe on a rough surface, regardless of the surface roughness, or for whatever surface roughness you want. That should account for these effects, basically, and it's not as intractable as it sounds. You know, with modern computers, we run a model overnight for the entire moon or something. You know, so it's not that big a deal.
Okay, for the moon is probably doable, but what about non-resolved objects like all these nice TPMs for asteroids, ground-based observations? Yeah? It's okay if you show curves, fluxes in millianskis or whatever, but as soon as you're talking about temperatures, you're talking about disk integrated temperatures of irregular, airless object far away. So this is even worse than a pixel on a resolved image or observation. So that's
two sums, right? You do the first sum,
yeah.
the facets within a big facet, and then you sum all the facets.
If you have a shape model, and if you know the surface roughness, which is below the level of shape model resolution, usually if you just apply Spitzer observation, if thousands of objects and you process it, and it's just a standard TPM, it doesn't really do all this. It cannot. So what do we do there? It's even worse. It's effective some things.
Yeah, but I think it's important to be aware of this problem. No? The second one is the thermal inertia. It's also my another thing I'd like to comment again, and so I must say, and it's also a tradition to work with thermal inertia, but going back to the 70s, when it was defined the first time for Mars, not for comets or so. For Mars, the thermal inertia was derived in a mathematical strong sense with some assumptions that are not valid for our business here. And one assumption for the thermal inertia is you have only quantities like heat conductivity or specific heat do not depend on temperature or depth. They must be constant. In other case, you can't derive thermal inertia. You can try it. It's impossible. And another point is that this is it's dangerous. I can produce you with the same one and the same thermal inertia temperature profiles. They are completely different. Yeah? And it's only valid for the surface. It's a small exercise. I can show it to you, but the leading parameter for profiles is the diffusivity in the thermal equations, and I can define everything. I can define rho squared times specific heat squared divided to density, and can publish it, but it doesn't help. It is from a physical point of view, it's senseless for the depth, because it's not unique. You can show it's for the surface, it's a perfect description of thermal inertia. And even if it's constant, it's one what must be. That's constant. But even if it's constant, I can show you that I can calculate completely different profiles with the same thermal inertia, because it's not the right combination of these quantities for the profiles. And this is my point with Miro, because Miro goes to the depths. For the infrared measurements, it's fine. Yeah? You have the surface temperatures and thermal inertia, and it's fine if you don't need profiles. But Miro needs profiles because the wavelength is too long for surface phenomenon. It goes into the order of magnitude of skin depth. And to describe Miro results with thermal inertia, for me, it's not very helpful, but it's my opinion.
Well, I mean, I agree that you have to specify all of these parameters. You can't just say the thermal inertia is X and then that's like the end of the story. You have to specify them all, and we do specify them all. So the way we use thermal inertia is it's a parameterization that basically is primarily because the density, the product density in specific heat is not something that's going to vary a lot between different materials and so on. But the thermal conductivity is something that does vary quite a lot. We felt it was a convenient parameterization for that, and it's something, I mean, every darn talk in this thing has put up thermal inertia with different letters specifying what it was, but so we're not quite as uniform as we are with geometric albedo, apparently. But you know, and what I found was that it was great because you know you could see basically intercompare all of these objects. It's true, you have to be careful about that. And one of the things that we found that was interesting was that if you model basically the density times specific heat and you allow that to vary with the density a little bit, in the end, because the thermal inertia is wired to the thermal conductivity so strongly, you got pretty much the same answer. So, I mean, at the end of the day, I don't really care how we tell you what thermal conductivity is, but this was a parameterization. That's the way I look at it.
Okay, thank you. Should move on, maybe. So Jens is going to write a paper with this discussion. Yeah. Because this discussion came along another time, so we just don't give a recipe. So we say these are the instruments. This is what people measure. Be careful because they can be different things, and be careful when you compare it to model that deals with the kinetic temperature, like sublimation of volatiles or thermal fatigue and so on. But yeah, it's okay. Because I think we should basically finish by 6:30, right? Like we did every other day. So next point I was thinking about is this thing, and maybe Alberto wants to comment on this, or which H magnitude we should use.
First thing is that to take into account that in 2012 IAU has changed the definition of photometric system for asteroids. The absolute magnitude is normally derived from an extrapolation of the phase magnitude curves, and the kind of curve that is supposed to hold for asteroids is the one that now is described by means of three parameters: H, G1, G2, whereas before 2012 it was HG simply. So the first thing to do is to use the new standard. So this is and then to take into account that the absolute magnitude of asteroids is not a fixed parameter because it depends on the geometric configuration that varies from one apparition to the other. This is something that I already said during my talk. So the ideal thing to do when one has at disposal a very large amount of photometric data taken at different epochs corresponding to different apparitions, different phase angles, and so on, should be to try to derive H values from different sets of data corresponding to limited intervals of ecliptic longitude, because this means that you are comparing, analyzing the phase magnitude in a range in which the geometry of the apparition is not changed very much. And so you can potentially find the different values of H, and this can even give you some information about the shape of the objects. This is something that was not possible in practical terms before, because we have not sufficiently good data with decent accuracy. But now, if we have, we are in the new era of large sky surveys from space or from the ground, using single instruments and so on. This is something that can be done. This is a tremendous work to be done. It will be. It's normal. And as for the albedo, okay, there are two different definitions. There is the geometric albedo and the bond albedo, but the definitions are clear. So it is only the point is only to use the right one for the problem that you are considering.
I think that the problem with albedo is the same with as with H value, because also albedo is not constant given to an object. It depends also on the geometry. It's uniquely defined only for a sphere, and if the shape is not spherical. No, we won't, because it depends on the like orientation of the surface.
Yes.
With respect to
so this will automatically adjust. If the object is homogeneous, the data will be the same.
I mean, geometric albedo.
Is that is the ratio between the brightness that is measured at the 0 plane, blah blah blah,
Yeah. Of a disk.
With respect to the flux that you would get from a Lambertian, ideal Lambertian flat disk having the same cross section. This is the definition of albedo. Or geometric albedo. Yeah.
So why do this MPC H magnitude suddenly become right at H equal 20 while they were wrong at H equals 14? What's the magic here?
I have an idea, but I'm not sure. So I think that Emmanuel, I don't know exactly, but I didn't read the paper yet. So I think here the objects are very well observed over many years. Over there, it's just the big surveys with CCDs that do a good job in doing photometry. They pick them up. Here in the middle, they're probably a little bit of everything, because I can even send magnitudes to MPC from my balcony with a Celestron 8. I observe an object here, and I send the magnitudes, but probably are not as good as those calibrated with 1 meter photometer.
But in this plot, each point is one asteroid.
I guess I didn't read the paper. Just the paper that came out. I heard about it because Bryce Bowling, one of the authors, is in our group in Nice now. But I didn't read the paper, so I don't really know.
So it's brighter because people think they have seen the object while they haven't, right? In your interpretation.
No, I think here is probably old,
and
No, but
good.
in the middle.
Here is a little bit of
Yeah, but why is it
wrapping.
systematically higher?
This is
Bec- yeah.
not clear.
Well, but this is
Yeah.
clear here.
No, it's clear in the data, but this bias is known since a long time, even before this paper, that there is a systematic displacement toward in this direction. But the reason for that is probably multiple and not completely clear today. But what I would stress is that beside the bias, you also have this big dispersion, which is much higher in certain situations than half a magnitude, which was already known. And this is a big concern for any use of H today.
One basic problem is that the magnitudes that are sent to minor planet center and are then published are generally obtained by people who are interested in astrometric observations. So these are observations that are aimed to make discoveries of objects or follow up. And the primary goal of this observation is not the photometric accuracy, but it is the astrometry. And so this is why there are so big errors in a large interval of absolute magnitudes. Then possibly the strangest shape is something that is well, it has to be understood. I mean, also for me, this is the first time that I see this plot. It is possible that, yes, in the left part, you have objects for which we have a lot of observations and also of good quality. And take into account that H varies, as I was saying before, but this is this. And then maybe at the right end, you have only the data coming from some single sky surface, which is not mixing data coming from different instruments that are always difficult to be put together. Yeah, filters. There are a lot of sources of errors in the determination of this.
Yeah, this effect was known since ever, and there's also this paper by Pravets et al. I forgot the date, I couldn't check, but he showed it very clearly, this effect. So this
between the photographic plane
right.
and the CCDs, there was a critical interval of time in which the new observations were not good with respect to the other ones.
Following up on this, the effect is important. So this problem is important effect on many things, including this. So, for example, when I saw Andrea Milani last time, and he published this paper where you are co-author, Milani et al. 2014. This is a paper by Federica Spoto, that is the Milani PhD student, but that study the age of the families. And basically, this is the distribution of the albedos you get from a family 20, which is Massali, which is an S-type, I think. It's pretty large, I would say. And the question that Milani asked me is this real or is this due to errors?
No, but if you consider that it used to be pretty large in all cases, you have to consider the fraction difference, not the absolute difference in albedo. If you go to the darker objects, you also have a full width of this distribution that in percentage is rather large. It's the same if you go from 0.2 to 0.6. I mean, 0.2, 0.5, 0.6 is 50% in one side. 50%.
Yeah, but my question is, do you think that improving the H's will make the histogram narrower?
I'm pretty sure that you will improve this.
Because it's better 50%, 0.2 can mean 0.1, 0.2. Sure.
Yeah. Yeah. No.
No, sure. But that's the only example I found in 30 seconds. There are others. There's like a Maziero paper that shows
and from a statistical point of view, the uncertainty is about 20%.
Any given family will always contain some amount of interlopers.
Yes.
So you can expect that they will have some wings. but the bulk of the family should be more.
And it's clear that the effect of the absolute magnitude is the principal reason you had this spread.
Yeah, there's another example here that is it would be worth studying if you can, by improving, if I can get my Mac behaving. So this paper this is the it's very small, but this is the Mazziero 2011 paper, the famous one where he put out the first Wise diameters. And so look at so these are albedo distribution of families. So he uses strange albedo range. So it's a log PV. So it's minus. Well, but it makes sense to use the log of PV. But the point is, as you can see, the Ungaria family is basically skewed to 1. So, okay, E-types are bright, but are they so bright? I don't know.
Well, exactly. If you had the spread due to the uncertainty in H, you can say nothing about the spread inherent to a family. The argument was Milani was that basically we cannot disentangle between something that is real and something that is a dispersion that is due to uncertainties.
I don't know if we know the spread of the uncertainties in the H value, we can disentangle both effects. You can translate the spread of in the absolute magnitude to an spread in albedos. You can assume that all the objects have the same albedo, and then include this spread in absolute magnitude.
The accuracy of H will improve the situation. But in any case, for a single object, the correct way to derive a very accurate albedo from thermal radiometry is to use thermophysical models. Otherwise, if you do something that use for all objects the same values of beaming parameter, whatever you want, there will be something due to the fact that some assumed parameters are not suited for this particular object, these kind of things. So it is an interplay of the very big errors in absolute magnitude in the visible and some factor due to the modeling of the thermal flux.
Just one comment about the sort of crazy logarithmic scale for the histogram. I think it makes sense because if you have for example a single object and you assume a diameter and you vary the diameter with Monte Carlo with a given sigma, and then you assume a value of h and you vary the Monte Carlo with a given sigma, you are going to get a Gaussian in that in log. That's it. So it makes it. Apart from that, it's very difficult to read the figure anyway. But it makes sense to use it.
It's too bad that Mazziero and Wise team is not here. Not here. Very bad. Anyway, so let's. Where is it? I lost my.
But I think that with the new surveys, this is a situation that's going to change very rapidly with much more accurate H values in the next years.
The problem then is to control the thermal flux measurements with the right visible data, because visible data also change. H is not fixed, so you should have to put together the data in the infrared and the invisible.
The absolute magnitude will change by alpha magnitude.
It depends on the size, on the shapes. If you are a sphere, it doesn't change, but you have something that is it can.
Yeah, but when you collect a lot of observations,
it depends on.
You have
Yeah, you do something that is an average of the different possible.
Point of view,
Yes, yes, it will.
for particular object, you need to have a shape model. You need to do it. Well,
Okay. More? No. So this is for you, Javier. You lead it because you wanted to talk about mission.
No,
how do we get ESA to approve a mission to a planet or to a asteroid or comet, whatever it is?
I felt that after I saw your slide on what's next with the after Akari, WISE, Spitzer, and so on, and say, okay, not only telescope but also space missions. What's going to happen? Because here in this room we have some people that not only work on models, also do some laboratory stuff and build instruments.
Yeah, Migo, for example.
So, what's going on with this?
Well, I mean, in terms of space-based infrared facilities, I think the future is not so bad because James Webb is coming up. Launches in 3 years, late 2018. There's going to be a couple of months of commissioning, and you know how these things go. But the first call for proposals is going to be 2017. So that's actually not so bad. And James Webb can do imaging and spectroscopy from, I don't know what the shortest wavelength is, but it goes out to 30-odd microns. So for asteroids in the thermal, it's great. Well, there's a problem with the near-Earth ones because it cannot slew or track nearly as fast as we would like it to. It's limited to, I think, 30 milliarcseconds a second is what the tracking limit is right now. Not necessarily. Sometimes they happen to be moving a little slower. Yeah, we do some twisting of arms then trying to get them to calibrate their tracking rates out to faster tracking rates. It's not looking very good at this point, frankly. So for near-Earth asteroids, that's just... Well, for KBOs, you don't really see any thermal to speak of, and you're on the Wien slope.
And what about Spica?
Yeah, I was going to get there next. This is a proposed mission, a joint mission between Japan and the European Space Agency. And if approved, that would launch in the late 20s or so. So this is way down the road. But this would be a great team to get KBOs right in their thermal emission. It would include one camera called Safari, and that does reasonably low resolution spectroscopy from 20-odd micron up to 200 or so. So it covers the emission peak of TNOs. It goes down reasonably far on the Wien slope to characterize the temperature very well. So it's much better than Herschel that way. Herschel only started at 70, so for PACS that was kind of too long for comfort. And it's going to be an order of magnitude or two more sensitive than Herschel was. It's the same mirror as Herschel, essentially, but cold. So this, however, is not approved yet. And this is actually a call for support from the people in this room. On the European side, there's going to be an M5 proposal that is probably due sometime next year. And I'm helping to work on the science case for the solar system for that, which is essentially KBOs. If anybody wants to help with that, I'm very happy. And yeah, like I said, it's not approved yet, and it's our job to get it approved.
Does anybody have news about NeoCam? Unfortunately, we don't have Amy here, but I think she proposed, right? Huh?
So yeah, I was on that team. I went into the discovery round, and they just haven't announced selections yet. I forget what they said they're expecting for that, like September or something. Yeah.
And the other stuff on missions is what and my proposal is partly because of the news I gave you earlier about the M4, and because some people here is working in building instruments, and I'm afraid that from the European side we have the missions that are flying now or ready to fly. We have a technological mission which is part of the AIDA mission, which is AAM. Sorry, I always confuse with this English pronunciation. I can change it. And there should be a thermal instrument there, but a very simple thermal camera, and that's it. So we will. I'm afraid we will not have many chances, at least Europeans, in the next decades.
I think in terms of going to asteroids, maybe not, but it's worth thinking about some of these science you can do on the side from some of the proposed things like Ariel, for example, which did win through today, could do. I mean, that's going to be essentially a light bucket spectrometer, no imaging, but it will give you spectra from, say, 0.5 to 11 microns. So if you can get time observing, opportunity time, as it were, then you could actually use one of these. It's a very photometrically stable, by design, spacecraft at L2 if it got selected. So it could be very effective for doing some quite nice spectroscopy of some of these objects. Certainly from, it covers all the sort of key, it gives you in a single, if it really is what it's supposed to be, it would give you in a single shot the thermal tail plus the large chunk of the thermal spectrum, the beginnings of the 8 micron region, and it would also give you all the near-infrared reflectance stuff that we like to work with from the ground. So if you could get the time, it could be quite a good instrument for doing this. Of course, the problem is it's not designed for doing that, and you'd have to worry about fluxes and the like. But there are quite a few of these sort of either L2 or other space observatory type instruments that are being proposed at the moment, which give you the opportunity to do some of this type of science. They're designed for photometric stability, so for doing light curve measurements and stuff like that, they'd be quite good. Probably better than JWST or something, which is going to creak and groan, I imagine. It's such a big thing. Though I don't know about JWST really. So, non-sidereal tracking is probably tricky, but I don't know. But the other option is that we just come up with a design that's cheap and go for an S-class, where you can do non-sidereal tracking, so you can put it in the right orbit around Earth or something, and if you don't care too much about thermal variation on the spacecraft, because you only need, say, 70 Kelvin detectors or something for doing thermal infrared work, or maybe 40 Kelvin, something like that, then there's no reason why you can't go to any target you want. So, for 50 to 100 million or something, you could probably do something, he says, making up a number. But, it's not dead, as it were. Yeah.
Thanks. Next
topic. Photometric emissivity. This was mainly following.
Come back to physics.
Yeah, and this was mainly following up on Josh Emery talk, and so while I was working in Berlin during my PhD, we were very happy because we didn't have very good data. But now that we have good data, we probably should care about this. So can we keep up using 0.9 in our TPMs and need them, or we should change? Let's vote. Let's vote. This is 0.7 at 5 micron.
Well, I think, the exactly.
Let's just put this, but it should be like more emissivity. I should have emissivity.
Right. So as we've talked about already, there are two places where emissivity enters into the solutions, and we all know this. There's the bolometric emissivity that's averaged over all wavelengths. It's averaged over the flux spectrum of your object, and so we use 0.9 or 0.95 because silicates emitting at around 300 Kelvin for almost all silicates, 0.9 or 0.95 is a good number. If you really have a metallic asteroid, then 0.9 is a terrible estimate because metals don't have an emissivity of 0.9. But so I think it's a matter of knowing what we're doing when we're modeling what it is that we're trying to model. And then the other place it comes in is what wavelengths you're making your measurements at, and so you have to know be realistic in the emissivity that you're assuming for that measurement where you're interpreting your flux in terms of some type of temperature.
67p. Yeah, take it. In fact, do we have any constraint on its bolometric emissivity? Or could it be anything like 0.3, for example?
Are you asking me?
Yes.
I'm not on any of the teams, so I don't know. But I mean, it's covered in dust, right? And so what we're seeing is emission from the surface. That's a dusty surface, presumably a silicate dusty surface. So I would think that 0.9 or 0.95 is probably a pretty good estimate. But you know, maybe
it doesn't depend only on composition, I suppose. You say it's dust, it's silicate dust, okay? But I assume it will depend on grain size and everything, all the radiative transfer inside the surface. What? Lots of what?
Carbon.
Carbon, oh.
Lots of carbon to bump up the emissivity plenty high at whatever wavelength you want.
Is it elemental carbon? Do you know?
Lots of different carbon. Yeah. Look at the Halley mass spectrometer results.
Yeah, but that's
maybe keep 09.
Let's convince the politician that there are diamonds there.
Well, our best estimate is probably measurements of meteorites, right? I bet somebody has done that measurement at some point in time, except I wouldn't know. What do we know about the bolometric emissivity of meteorites? Everybody's shaking their hands. That's interesting.
I'll show you some plots. Sorry. I'll show you some plots tomorrow.
But we never have eroded surfaces of meteorites.
Yes, sir.
We also use 0.9 for satellites, which may be not good.
I don't know anything about what ices look like, especially if you have an icy surface of 170 Kelvin, what that would be. So we can compute a spectrum of ice and integrate it. I have an answer by tomorrow morning, but I don't know who that person is.
Okay. That's it. So this is perfect for next topic. We have 2 minutes to discuss the rest. So I think the message to take home is that we keep 0.9. Right? We're happy with 0.9, and then we take a little. Yeah, we're careful, and when we look at some object, if it's a metallic, we find a thermal inertia of 1,000. Maybe maybe we should revise our emissivity, something like that. Okay. Sublimation and TPM. Cedric, you want to start with this? Mike.
I'm not sure if I'm right, but I just found that most of the simple TPM use sublimation at the surface by just adding a boundary condition for the surface, so that you can eject some artificially eject some heat up to the space. But if in the comet, for example, we detect dust at the surface, and below probably water ice, and then CO2 ice below the water ice. So if we want to include sublimation beneath the surface, such boundary condition is not enough, because we have to add some mass transfer from the bottom part to the upper layers. Is this right?
I don't know TPM of comets, but so don't look at me. Oh, I know from yeah.
Well, I mean, there are people that are running those kinds of models too. I mean, I don't happen to be one of them, but there are some of my colleagues are running those models and treating a layer and then treating the sublimation as coming from below the surface. And I mean, it's the models like Prialnek and so on, and other groups have done. So my own bias has been that, you know, what's our evidence that that actually takes place, right? So it seems to me one of the things we wanted to do with Rosetta was to show that that kind of surface structure exists, because that's basically what everybody said ought to exist for a long time, that there should be mantles, you know, there should be these layers and so on. So, I mean, in my own look at the problem, what I've been trying to think about is how can I prove that that's the structure, not infer that, not basically adopt that structure and solve for the parameters of that model, but rather what is it in our data and the Virtus data that can prove that that's what's going on the surface.
That's exactly the problem, and I've shown you this model calculations this morning, and what we saw in the actual Virtus fluxes and also the Moreau data was very immediately clear that the models that assume exposed ice on the surface are not right. So we discarded them altogether. But that's too simple. We also saw with Virtus that was in all media, there's no ice on the surface, or only very, very little, or maybe 1% in the Harpy region. But that's, again, based on a very big pixel size where you integrate over everything. And you're looking for signatures of ice absorption, and you don't see it, or only very faintly. But it could be, looking at the close-up images by the lander, that this material is rather inhomogeneous, that you have veins and patches of maybe ice. We have found some patches like fist big that are significantly brighter, that are inside of some other material which is more, you know, maybe less or devolatiles, without volatiles or something else. Or there are cracks and layers of material on a large scale, on 10 centimeter scale, that is look very different from this. Not homogeneous, this stuff. So if you have, like on a chessboard, 100-meter square area typical footprint of a remote sensing infrared or microwave instrument, and you have patches of icy boulders everywhere, close to the surface, with only a few tens of micrometers of dust on top of them, just dust everywhere. Then you don't see it, because most of the signal is coming not from these icy patches. So you cannot really conclude, I think, that there's no exposed ice on the surface. Not so easy, because it can be much more inhomogeneous than we think. And I also believe that the simple picture of this classical layering, then first the dust, then there is dust plus water ice, and there is dust plus CO2. This doesn't really work. We have, if you look at the Rosina data, the mass spectrometer, are very sensitive to gases. Yeah? As soon as the sun goes up, they measure CO2 immediately. There's no lag. You would expect a lag if the thermal wave would need some time to penetrate through the dusty layer in the standard model to reach the CO2 volatiles and then to trigger the CO2 sublimation. It's even detected in the night. Yeah. But it's mixed. There's a component that is always there, and there's a component that is correlated with the phase angle of the sun. And okay, then again, this instrument is more or less hemispherically integrating, so as that you get very many different things overlaid. Mm-hmm. Oh. Yeah, but the diurnal layer is only a few millimeters. And the grain size may be of the order of 1 centimeter. The grain size of the regolith material.
Okay, here we have some people that is starting to sublimate, so. And I will not repeat Marco's song.
We can talk about these M-type astro. We can talk about last thing. Sorry for skipping. Zoe, we can talk about M-type, or we can skip it for later. This is I like to briefly discuss this because this was
kind of provoked by Stephen yesterday, and it's interesting to me. How can we explain it?
Yesterday, the observational bias was mentioned because when you observe asteroids that are rotating very fast, you can suppose that they are being accelerated. And if you don't observe those low ones, on which the effect is much difficult to detect, then you don't have them in the sample. But it's just to recall an argument that was given.
Yeah.
I was interested in this discussion. Just to readdress the question that was asked, could this be a selection effect? I didn't quite answer the question properly the first time. You have to remember the idea of Yorp cycles. Do Yorp cycles exist? Okay, the statistics are small at the minute. There's probably 5. I think the eager will ultimately prove to be another positive spin out, and say that one's the most tentative one at the minute. So you've got 5 that are all spinning up. So there's a 3% chance of that happening. So let's just say that Yorp has an equal chance of either spinning it up or spinning it down. So you would expect, if you had a wide enough sample over a wide enough, kind of asteroid, long period spinners versus short period, you would probably expect maybe half to be spinning up and the other half to be spinning down. But let's just say there is a partial selection effect in that, whereby in the case of our survey, we were picking those asteroids that are rotating fairly fast because they were very practical for observing and all the rest of it. Okay, so I think that's true. There could be a partial selection effect there, but if Yorp cycles are really happening, then why would all of them be heading in the same direction? You would expect some of those to be heading the other way, and the same goes for asteroids that have very long rotation periods. There's no reason to say that if Yorp cycles exist, that all of those are heading towards longer rotation periods. You would expect some of them to be coming the other way as well. So we don't know what the statistics of that is. It would require more modeling, I would say, to give us an idea of what those statistics and probabilities are. But I think we're at the point now where the statistics are starting to get very interesting. We just need more. But if this trend continues to 6, 7, maybe 8, then we really have to start looking at the physics of the Yorp effect, the tangential Yorp being a really good, an excellent place to start now. I hope that makes sense.
I'd like to add that we still don't have a complete understanding of these Yorp cycles. What we have now, this classical picture from Bravich 2008, I think, is one-dimensional. It doesn't include the evolution of obliquity of asteroids. It doesn't include the tangential Yorp. I don't believe that tangential Yorp is the most important effect, and that it can be responsible for all this happening, all asteroids spinning up, but probably it might be important in some areas for some specific asteroids like Itokawa, who are relatively symmetric in terms of the normal Yorp, and for some rotation periods where we get this thermal resonance. So we need to go two-dimensional, and in this two-dimensional scheme, we can obtain some new physics, like not only asteroids led up to their breakup, or asteroids stopped and caught in tumbling with very small rotation, but also in between, as an interaction of the normal and the tangential Yorp effects. It might be possible that some asteroids are just caught in a stable rotation state, in stable equilibrium, where they neither spin up nor spin down. It's possible in theory, and I'm very interested, and this question goes to Steve, if from our observations up to now, we can conclude, expect that we have too much asteroids with negative Yorp detection. Can it be that up to now we have detected too little Yorp accelerated asteroids because of some asteroids being caught in stable rotation?
I'm not quite sure how to answer that. Okay, we've got, let's say, for argument's sake, we've got 5 positively detected. Let's just take 5 as being the number. There are several non-detections. We can't really take the argument much further than that. We can't really, until we have a better fix, I guess, on Yorp theory, where we can go to a given asteroid where there's a sufficiently good shape model to say that the Yorp effect should be this strength, but the observations would show that it hasn't been detected yet, then we can start to address those kind of statistics, if that makes sense.
I guess the modeling challenge for now is to get the observed strength of the Yorp effect in those 4 cases where we have it constrained empirically, to get that modeled right. And I don't think we're there. In the one case where we have the shape model that is good enough, that's Itokawa, if you take that at face value, you even get the sign wrong. That's your talk, right?
Yeah.
I think we have a big problem with the models here.
Yep, absolutely, absolutely. But getting observations is part of that. It's part of all that whole puzzle. But yeah, I completely agree. The modeling needs work.
And I'd like to add that the worst thing for Itokawa is not that we get the sign wrong, not that it is maybe the tangential Yorp or center of mass shift, but the most disturbing thing for me that the normal Yorp predicted from different Gaskell models with different resolutions don't converge when we go to very good resolutions. And it probably means that either the Yorp effect is extremely sensitive to small roughness on the surface, which doesn't seem to be probable, or that something is wrong with these models, that there is some east-west bias intrinsically included into these models, because the models were not designed for Yorp calculations, and the authors just didn't care of this. And for example, when they had an opportunity to draw a facet eastwards, westwards, the program intrinsically chose one of these possibilities with a higher probability, something like this.
If I remember well, apart from Itokawa, all those 4 asteroids for which there is a Yorp detection, the value predicted by theory based on radar or convex inversion shape, they agree pretty well with the empirically detected value.
Speak close to the mic because there are people listening on YouTube.
So again, that the value predicted by theory based on the shapes derived from light cars or radar for those 4 asteroids, they agree with what was measured. So for those 4, there's no need for T-Yorp. It can be explained by this classical Yorp, and the values agree.
Yeah, I guess I'll just follow up on Joseph's comment, really. It's that if you consider the 5 Yorp-detected asteroids and you normalize the Yorp strengths to a common size and diameter, you basically find that Apollo has the strongest Yorp effect. It's probably between 10 to 100 times greater than that detected for Itokawa, and that's mainly driven by the large scale shape asymmetry. Whereas Itokawa, the large scale shape asymmetry pretty much cancels out, and it becomes sensitive to the small scale roughness, which is why the gas star shape models don't really converge. So, so if you basically find, I think basically what we need to do is like normalize the detection to a common size and diameter, and then basically we'll find that the really strong Yorp detections are really are less sensitive to the details of the shape, whereas the weaker Yorp detections are really sensitive to the small scale stuff. And yeah, and to tangential Yorp when they're weak, but when they've got the strong shape effect, and that will dominate over T-Yorp. That's my take on it. So.
Yeah. Can I just have a quick comment? Sort of building on Joseph's comment. In the case of 2000 PH5, the corresponding theoretical prediction that was published alongside that result was between a factor of 1 and 7 times what was actually observed. Now, at the time, we considered that actually a success because it was in the right ballpark of where it should be. But what we really need to do is use high-resolution shape models when we can. I think that's where the real leaps in reconciling observations with theory is really going to happen.
Okay. Oh, yeah. So thanks a lot. Thanks a lot. A very nice round table. And now it's time to rest a little bit. And at 8:30, met here. It's not the same restaurant. It's the next one in the same floor, where the billiard and so on. Please remember to bring your ticket. It's just an identification for them to know who is fish, who is meat, who is vegetarian. Don't stress if you forget it, but please try to bring it with you. Okay? Thank you very much. Thanks to the speakers. Thanks for everybody.